slightly differently.
Did we graph logarithmic functions last
We
year?
graph them the first way that we'll graph, but then we're going to graph them a different way. So we'll kind of go over, yeah, this is how we graphed last year, but we're going to graph it slightly differently. Different thought process. Gotta make sure, Brandon, that you're learning something new about logs, right?
Yeah. I like how calculus solve problems. They weren't too hard, but you had to think to understand. Once you understood what the problem was asking you to find, it was really easy.
Come on, buddy. All right, so -2, -1, 0, 1, 2 would be the common numbers that we pick for x. And Virginia, when you plug them in for the exponent of 3 to the x, what do you get out for y? So the negative exponent always makes a fraction. And then we can plot these points. And it gets increasingly large pretty quickly. That distance between 3 and 9 then goes up to 27. So that's what makes it an exponential function. It grows at an exponential rate, which means it grows pretty quickly. And this has an asymptote at y equals 0. So Libby, is this a function?
Yeah.
Yes. Passes the vertical line test. Is it 1 to 1?
Yes.
Yes, which means it passes the horizontal line test, so does it have an inverse?
Yes.
Yes. If you said no to one of the above problems, then you can't find an inverse. If it's not a function, you don't have an inverse. If it's not 1 to 1, it doesn't have an inverse. So it must pass the horizontal line test to have an inverse that's also a function. So that's what that last question means. If it's 1 to 1, yes, so therefore the inverse is also a function. So inverses we talked about in chapter 1. Little bit of refresher here. The domain, which is really x, of your regular function becomes the range of the inverse. Because if you're finding an inverse, what are you doing? Flipping, switching?
You're flipping your x and y values.
Yeah, you're switching the x and y values. That's how you find an inverse. You take x and y and you flip-flop them. So if we're talking about domain and range, they're going to flip-flop as well. So if it's the domain of the regular function, it's the inverse. The range is the inverse. And if you have the range of the regular function, then it's the domain of the inverse. So they flip-flop. So the range becomes the domain, or x and y change. That's how you find an inverse function. So we're going to take that information and try and help us graph a log function. Little definition here. So it says logarithmic functions to the base a. Last year we used the base b. Now we're using the base a. It doesn't mean any different. Just we usually have a base of, I guess, an a. In this case, we've used that a lot. So we had y equals ax squared plus bx plus c. We had y equals a times the absolute value. So that a is that common variable that we're using in a lot of our functions. So a is now switched to the base. So f of x equals log base a of x, where our base, that little guy there is the base, is greater than 1. So the base is positive.
Would you work it wrong if, since I'm used to saying log base b, would you work
No.
it wrong if I put a b?
So underneath, as a reminder, the domain of the log is the range of the exponential function because they're inverses of each other. The range of the log is the domain of the exponential function because they're inverses of each other. So using these facts, we are going to try and graph y equals, or f of x equals log base 3 of x. So from above, we just graphed y equals 3 to the x, and these are the numbers Virginia gave me. How can we graph log base 3 of x? Brandon?
You can change it back to regular form, and wouldn't that be y equals b to the x?
which I have over here. Right, so we just flip-flop the x and y values. So he is right. So if you think about log base 3 of x as an exponent, it's 3 to the x power. So those two functions are inverses. If the base is the same, we have the same base as an exponent, the same base as a log, they would be inverse functions. So in order to graph log base 3 of x, we literally take our exponential function and switch the x and the y. So if it was x, it's now y, or if it was the domain, it's now the range. So the x values are now all of our y values. The range values become our domain values. And that's how we graphed these last year. So we thought about the inverse function as an exponent. We plotted or kind of thought about the values for x and y of the exponential function, and then we flipped them to get the log function. So when we graph, the x is now 1/9, and we're going down to -2. And then at 1/3, we're down to -1. And at 1, we're at 0. Where before we had a point at 0, 1 for the y-intercept, now we have an x-intercept. So this graph should skim along the y-axis, whereas the graph above skims along the x-axis.
Is there a slant asymptote?
Not a slant asymptote. There is a vertical asymptote.
Oh wait, I was thinking of something else. Inverses have symmetry along x, y equals x.
Oh, like the two if you compare them together.
Yeah, right?
Yes,
Okay.
yes. I don't know why this is not calibrated correctly. So if we compare them together, they have symmetry over the line y equals x, exactly. So this flipped over that line, and that's why we have it in the third quadrant. Yes, Brandon, that part is right. So if you look at this graph, its domain goes from, Sabrina, do I take the pass? Sure. So what's this domain go from? Brandon? 0 to infinity. The range, Brandon, would be? Right, negative infinity to positive infinity. Which were flip-flopped for the exponential function. So the exponential function has a domain of negative infinity to positive infinity and a range of 0 to infinity. So they're flip-flopped. This one has an x-intercept at 1, 0. And it doesn't have a y-intercept. So inverses, literally everything switches. So an exponential function has a y-intercept at 0, 1, but it doesn't have an x-intercept. And this is the exact flip. And then now we have a vertical asymptote, whereas the exponential function had a horizontal asymptote. So your asymptote flips because one was y equals, this is now x equals, x and y switch. This graph is still increasing because the original graph was increasing, and it is 1 to 1. So if your original graph starts off being 1 to 1, your inverse graph will also be 1 to 1. Questions? So one way you can graph a log, besides relying on the calculator, is to graph its exponential function, or just to find a t-chart for the exponential function, and then flip those ordered pairs. We're going to learn a second way to graph it, but before we do that, we have like some properties to talk about. We have to review conversions, review how to kind of solve little equations, and then we'll talk about another way to graph. Any questions with that graph? So, in the box at the top of the next page would be the two conversions to go from log to exponential form, or exponential form to log form. So if you start with a log equation, that equation could look like y equals, or f of x equals, log base a of x. And last year we used log base b, but changing it to an a. Its exponential form, or equivalency, is x equals a to the y. So the thing to remember when we're trying to switch back and forth, the a is the base in both of these. So the base of the log and the base of the exponent are the same. That really isn't changing. It's the x and the y that are flipping. So it's log base a of x. In exponential form, it becomes x equals a to the power of y. So they have to flip to be inverses, but the base is remaining the same. So a little review here. We have log form. See if you can convert it to exponential form. Once it's at an exponent, your equation should make sense. Like it should be equivalent. The left side should equal the right because it's an exponent. And it makes sense to you when you're looking at it in exponential form. So this is just rewriting, taking it from the log and writing it as an exponent. So Libby, do you think you could change log base 4 of 2 equals 1/2 as an exponent?
So it would be 2 equals 4. You could do square root or just over.
Exactly. So she said you could do square root because the 1/2 power is really the square root, or you could keep it as 1/2. But the square root of 4 does equal 2. So the base is 4. Here's the base. That base is staying as a base. It just now has an exponent. And that x and y value have flip-flopped. So 2 is equal to 4 to the 1/2. Eris, how about letter B? Log base 3 of 1 equals 0.
So you have 1 equals 3.
What's the exponent?
Oh, 0.
Yeah.
Yeah.
Did you say that?
I got very confused
No.
for a second.
Does 3 to 0 equal 1?
Yeah.
Yeah. Yep, that's right. So 3 is the base, the exponent is 0, and it's equal to 1. So Virginia, log base 2 of 32 equals 5 becomes, does 2 to the 5th equal 32? Yeah, so 2 times 2 times 2 times 2 times 2 equals 32. So that's converting it into exponential form. The next 3 examples want you to do the same thing, but then solve for x. So now we're converting it to exponential form so that we can solve for the x in the equation. So, Grace, how would we convert a to an exponent? We'll start with that first.
You're going to 10 to the x equals 1.
All right, so if you have a fraction, what kind of exponent must you have to create a fraction? A negative exponent. So x is going to be -2. So because it's equal to a fraction, your exponent has to be negative. Because 10 squared is 100, but 10 to the -2 is 1 over 100. So a negative exponent is how we get something to be a fraction on the other side. Brandon, can you convert b?
Yeah. 3, wait no, x equals 3 to the 3rd.
Sure. Or you could have said, you started out with 3. You could say 3 cubed equals x, or he said x equals 3 to the 3rd, which is
27.
27.
And you need one question.
Yeah.
So, could you use logs in transferring it to find the square root of like 416?
Yes. That's what, yes.
There were logs.
That's kind of like, yeah, how do you get one versus the other? Because you're taking 416 to 1/2 power.
Thankfully, they accepted just the square root of 416.
Yeah, well, you kind of need a calculator to help with some. All right, the last one, Alice. We log base x of 2 equals 1. That would become
So it would be 2 and then 1 to the x.
2.
I'm sorry.
X, how about x to the 1?
Yeah. Yeah. I don't know what I'm saying.
Okay.
Yeah, so x equals 2.
X equals 2. Questions? All right, the next 3. 4. I want you to write it in logarithmic form. So we have the exponent, the one that visually looks like it makes sense to you. You're used to seeing something written as an exponent. Convert it into a log form. So we have 8 squared equals 64. So Chelsea, written as a log, would be?
Log base 8, 64 equals
Okay. So remember, the base is still the base. It's just written in log form. So the 8 is the base as the exponent. The 8 is the base as the log. The x and the y, the exponent and the number on the other side, flip. So log base 8 of 64 equals 2. Michael, how about letter B? 9 to the 3 halves equals 27.
Log base 9, the 27, and then equals 3 halves.
Good. So the base is still 9. It's the x and the y that are flip-flopping. And Kayla, how about letter C?
log base 10, 0.001 equals 7.
And the last one. Gotta throw in that e guy. E to the 0 equals 1, Alice. How do we write that?
The natural log,
It is the natural log.
and then it'd be 1 because you don't really have to write the
Yeah, we don't really have to write that e there because the natural log only goes with e. So you don't need to write e there because it's always there even though it's not really there. And then that's equal to 0. So the natural log goes with no other number. It goes with the natural value e, the natural number e. So you would never have a base of 5 with the natural log because then it's log, not ln.
Then you did something, if you got that, then you did something wrong.
Yes, did something wrong. So every time you have an e, if you want to write the base, you can. But you will not see that base written. Every time you have natural log, it's there. It's just invisible. It's just like having x squared. You usually don't write 1x squared. You just write x squared. The 1 is always just sitting there. You just don't see it. All right, at the bottom. And then we're going to get into some actual good log problems. Require a little bit of extra thinking. At the top, it says the natural log of x would be equivalent to x equals e to the y. So those would be the two conversions there for y equals ln x or x equals e to the y. That's just a little review of natural log. So underneath, just to kind of give you a little bit of calculator work, when you're using the calculator button and you press the LOG button, which is on the left side, that's called the common log. That always has a base of 10 whenever you use that calculator button. So if you're evaluating for a log with a base of 10, you can hit that button on the left-hand side of your calculator. Underneath that button is the ln button. Anytime you see an ln, you hit that button and then you type the 2 in to evaluate the natural log. So the common log has a base of 10. If it had any other log, any other base, you couldn't use that function in the calculator. So the log base 10 of 10 is just, Chelsea? 1. Yeah, we'll talk about why that's 1 in a minute, but the log base 10 of 10 is just 1. 2 times the log base 10 of 2.5. So you do 2 log 2.5. Chelsea, what do you get there?
0.796.
Letter C says the log base 10 of negative 2. What's that one?
There's no number.
Yeah, so we can say it's undefined. Does anybody remember what we said the domain of these graphs were on the previous page? What's the domain of log functions? Virginia? 0 to infinity. That 2 is the x value. That's not in the domain. So you can't evaluate a log of a negative number because it's not in the domain of logs. Logs start at 0, they go to infinity. That's why that is undefined. Doesn't exist because negative 2 is not in the domain. So then the last three here, the natural log of 2. Chelsea, what do you have for that one?
0.697.
The natural log of e squared, this one's kind of nice. This is just 2. So natural log of e squared is just 2. Again, we'll talk about why that's happening in a minute. And then the last one, the natural log of 0.3. It's point. You remember this one, Chelsea?
Negative
1.22.
0.
4.
Yeah.
Yeah. Okay. just to kind of look at properties of logs, which we really didn't focus on last year. Using properties of logs enables us to evaluate, condense, reduce without converting it to an exponent. So without us trying to do the conversion and always relying on exponents, there are specific properties of logs, and I have them written on the sideboard as well so that we can kind of refer to them. But we're going to try and use these properties of logs to help us graph, to help us evaluate without translating it to exponential form. So the first property says the log base A. That can be anything. It could be a base of 7, it could be a base of 15, it could be a base of 79, whatever happens to be your favorite number. But the log base A, any number, of 1 is always equal to 0. And I want to show you why this is true. Brandon, why is that true?
Because if you change the forms to be 1, it equals a to the x. Well, the answer is always 0 then. Any number to the power 0 is more.
Right. So the reason that holds true is because any number to the 0 power is always 1. So that means whatever you have as a base, as long as you have a 1 there, your answer is always 0. So the log base 7 of 1 is 0. The log base 100 of 1 is 0. The log base 1,000 of 1 is 0. So the log base anything of 1 is always 0. The next one says the log base A of A is equal to 1. So thinking of this as an exponent, just to show you a little check, if I have A, that would be equal to A to the first. The base to the exponent would be equal to the number sitting next to the log, which is true. A to the first is really just A. So the log base 7 of 7 is 1. The log base 25 of 25 is 1. The log base 100 of 100 is 1. So when those two numbers are the same, then it's 1. The third one deals with having those two numbers the same, but that second value written as an exponent. And again, showing you how it works, this is really saying a to the x equals a to the x if we were writing it as an exponent. So whatever power the exponent is, to keep it equivalent, it has to be that same power on the other side. All three of those properties hold true for natural logs as well, which is why letter E, we have the log base E squared, or the log of E squared, goes along with this property here. So if I have the log of E squared, we said that was equal to 2. Whatever the exponent is what your property simplifies to become. So if we had the log base 3 of 3 cubed, if the exponent's cubed, it simplifies to be the 3. The last property is just like a little equation property. If I have the log base A of some number, that's going to be equal to the log of the same base of y, so that I can try and solve for those. So I wrote the properties on the board there, the first 3, because those are the ones we're going to use the most often, just so that we can try and look at the next couple examples and solve them without a calculator, without converting. There we go. So our goal is to not really convert to exponential form, but to rely on those properties of logs. So the first one says the log base 2 of x equals the log base 2 of 3. So Virginia, this just means that x is equal to 1. So what's x equal to? Nope, we're not changing, converting, we're keeping it as is. Asia?
X equals 3.
Yeah, x just equals 3. So if I go to that last property, which is somewhere on my screen, here it is. So as long as the base is the same, then x equals what? So x equals 3. We usually look at that as if it's like an expression and we'll solve for something a little more in depth, but 3 equals 3. The log base 2 of 3 equals the log base 2 of 3. Alright, looking at letter B. Again, not changing the way it's written, keeping it as the form, comparing it to one of the properties. Brandon, which property does this log base 4 of 4 go to?
Property 3.
How about the one above?
Oh, wait, 2.
Yeah. So this is log base A of A, which is just equal to 1. So when these numbers are the same, it's equal to 1. No work necessary, relying on the property there. The third one, we have natural log of 1 over e. Now we're going to do one little thing with this. How could you change the way 1 over e is written? Chelsea?
E to the negative.
Yeah, e to the negative 1. because then it applies to the third property. Whatever the exponent is how it simplifies. So if I have the natural log of e to an exponent, the exponent is the simplified value. So letter D is just 2. Letter E is just 0. And then the last one for letter F, look at your 3 properties. See which one of those properties applies to 2 times the natural log of e. Which one does that apply to? Alice? Yeah, because the natural log of e is equal to 1. So this is taking 2 times 1. That's what the natural log of e is equal to. It's 1. So this is really 2. Okay, so we're going to use these properties. This is like the tricky part of the lesson, to try and graph. So I don't want you to convert to an exponent and use the exponent and flip the x and y values and try and graph with an exponent. We're going to try and graph with the properties of logs. So the last question here, we have the log base 2 of x plus 1. So we'll make ourselves a t-chart, but we're not graphing this as an exponent or thinking about it as an exponent. We're going to try and use some properties. So when you're looking at the properties, and I wrote these over here so that we had them to use to look at. I'm in a different color. The number that's next to the log is your x value. So this represents x. Whatever number you plug in next to the log is really what's going in your t-chart as x. So the easiest number that I could use for my x value would be, that would be my y value. X value would be 1. So if I choose the x value of 1, that goes with the first property. So I'm going to put a little bit of work here so you can kind of see what we're looking at. Log base 2 of 1. Because I just chose x to be 1. Here's my x. And then plus 1 is kind of separate from it. So Brandon, the log base 2 of 1 is 0. Okay, so that part makes 0. That's why we chose the number 1. And then you're taking 0 plus 1 because this graph is shifting up 1. Therefore, your y value is 1. So we picked the value of 1 because the log base 2 of 1 is 0. So now I'm going to go down to the second property. The log base a of a. So whatever the base is, that's the number we want to pick for x. So Chelsea, we're choosing a 2. Okay, I'm going to show a little bit of work over here. So log base 2 of 2 plus 1. So Chelsea, the log base 2 of 2, the middle part there is equal to 1. And 1 plus 1 makes 2. Okay, so now we use property number 2. Now we're going to move down to property number 3. This one's a little different. So we have the log base 2 of 2, but we need to make an exponent up here. Because that exponent then is what my answer is. So, what exponent would you like to choose? No, Virginia. 2. So Virginia, your x value is really what? 4, because 2 squared is 4. So this whole thing represents x. But we have to write it as 2 squared so that we can use the property. Because the property says the exponent would be the solution, or the simplified form. And then I still need to add 1. All right, Virginia, pick another number for x. So we have a base of 2. So 8. So 8 means we would have 2 cubed. So 8 is 2 cubed. They're the same number. We're just writing it with the base of 2. The exponent is 3. So that's what that's equal to. And then we still need to add 1. So we get a 4. We're going to pick one more number. I want you to pick a negative exponent, not a positive, so that we have a different number to think about. So 2 to the what power? Pick a negative exponent. Brandon?
-5.
Can you pick a smaller negative exponent?
-1.
Okay, thank you. Brandon, what is 2 to the negative 1 so I can write it in my t-chart? 1/2. So my x value is 1/2. This is negative 1. Nope.
No, 0.
Yeah, 0. So the inside part is negative 1. Negative 1 plus 1 is 0. So that is totally different thinking. Like it's weird, it's different, but I'm relying on those properties and the bases. Like it really focuses on the bases and the properties. So now I'm going to take the t-chart that I have and graph it. So a 1, 1, a 2, 2, 4, 3, 8, 4, and then we have that guy at 1/2, 0. And I want you to get a negative exponent just so that you can see that it is kind of creeping along that y-axis. It's a lot harder to think about as the property of log. Like your brain eventually will get trained to think that way. It is a different type of thinking. So I kind of skipped over the domain, range, vertical, asymptote, x-intercept. You can write those down at the bottom left side of your page. But the next page in your packet, just like yesterday, there is a worksheet that has you graphing logs. I will have time to check homework tomorrow, I promise.
You don't have to.
When you're graphing logs, I need you to think about those properties, and especially for some of them, you're going to need to put some work. And there's space there for you to have your work. But you really have to think, like, what does that property do? What number do you need to choose based off of the base? Some of them will require a little bit of extra thinking than others, especially I think once you get to like 4 or 5, the last handful of problems. So I would really like